Welcome to this video on unitary evolution, the physics of information conservation and deterministic quantum states. Quantum mechanics is often associated with randomness, but this only occurs during measurement. When an isolated system is left alone, its evolution is perfectly deterministic. This predictable flow of the wave function is what we call unitary evolution. We begin with Part 01, the core principle, exploring why probability must be preserved in quantum mechanics. The law of survival states that if we have a particle, the chance of finding it somewhere must be 100%. Logically, the particle cannot vanish over time, meaning the evolution must keep the total probability exactly at 1. This conservation is the physical anchor of unitarity. Mathematically, the probability of a system is the inner product of the state psi with itself, and this inner product must remain constant if the system is isolated. Next, we move to Part 02, the operator U, where we define the quantum propagator. We introduce the time evolution operator, capital U. It acts as the mathematical engine of change, transforming the initial state at time 0 into the final state at time t. Part 03 is dedicated to the derivation, providing a step-by-step proof of the unitary evolution. Step 1 is the master law, starting with the time-dependent Schrödinger equation. This fundamental law describes how the quantum wave changes over time. In Step 2, substitution, we plug the operator definition of psi into both sides of the master law. This helps us find a rule governing the evolution operator U itself. Step 3 involves removing the initial state. Since the initial state at time 0 is constant, the derivative only acts on the operator U, resulting in a differential equation for U. Step 4, the integration. We solve the first-order differential equation for U. The rate of change of the evolution operator is proportional to the negative imaginary unit times the energy of the system. Assuming the Hamiltonian is constant, the final solution for the time evolution operator, ut, is an exponential function. This is the master formula for quantum dynamics. Part 04 focuses on the unitary property, defining the adjoint and inverse of the operator u. For probability to be preserved, the operator must be unitary. This means the conjugate transpose of u, called u dagger, multiplied by u, must equal the identity matrix. To find u dagger, we take the complex conjugate of our exponential solution. This flips the sign in the exponent from negative to positive. Physically, u dagger represents moving backwards in time. The unitary property works because the Hamiltonian is a Hermitian operator, meaning the energy must be real. If the energy were imaginary, probability would either decay or explode, which is physically impossible. Part 05 explores perfect reversibility, confirming that no information is ever lost in unitary evolution. Because U is unitary, there is no erasure. We can always work backward from the final state to find the exact initial state. Information can be hidden via entanglement, but never destroyed. We conclude the core of the video with Part 06, the physical meaning, connecting the mathematics to existence. Unitary evolution can be visualized as a rotation in the high-dimensional Hilbert space. The state vector simply turns. It never grows or shrinks. The Hamiltonian dictates the axis of this rotation. The Hamiltonian is the generator of time translation. Higher energy systems evolve their state more rapidly, rotating faster in the complex plane. Between measurements, the universe is perfectly deterministic. If the starting state and energy are known, the future state is predictable with certainty. Randomness only appears when an observer interrupts the unitary flow. Unitary flow is perfectly conserved and reversible, characteristic of an isolated system. Open systems, however, are non-unitary. Information leaks to the environment and entropy increases. Finally, we consider Part 07, real-world impact, looking at how unitarity is used in technology. In quantum computing, every logic operation or gate must be represented by a unitary matrix. This means quantum computers are reversible, allowing them to process information without losing consistency. This brings us to the break in the flow, decoherence. Decoherence occurs when a quantum system interacts with its surroundings. This interaction effectively performs a measurement, breaking the unitary evolution and causing the system to behave classically. Unitary evolution demonstrates that the foundation of the universe is a stable, deterministic ripple. Reality is a rotation of possibilities that remains constant until observation occurs. To recap the derivation, U is the engine of change, related to the system's energy. Integration results in an exponential form, and unitarity ensures probability remains exactly at 1. Mathematically, unitary operators form a group. This guarantees that successive unitary evolutions always combine into a single unitary evolution. Evolution from A to C is equivalent to A to B, then B to C. Any operator that is an exponential of an imaginary number times a Hermitian operator is guaranteed to be unitary. This identity confirms why the Hamiltonian must be Hermitian for physics to be consistent. Unlike classical logic gates, where information can be lost, quantum gates are unitary. This means quantum logic is perfectly reversible, and information is never discarded. In the Schrödinger picture, U evolves the states. In the Heisenberg picture, U evolves the physical operators. Both pictures yield identical physics. Unitary evolution is continuous. The state transitions smoothly through every intermediate step in Hilbert space, unlike the instantaneous jump of measurement. In conclusion, unitary evolution is the deterministic backbone of quantum theory. It guarantees that information is never created or destroyed in an isolated system, linking wave mechanics and thermodynamics.